Hello, my name is Ben Nell, and I will be presenting our paper published in IEEE Transactions on Antennas and Propagation, titled Q-Factor Bounds for Microstrip Patch Antennas. This work is done in collaboration with Skrivervik and Gustafsson. So before I start, let's quickly recap what a microstrip patch antenna is. So you have a patch on top of a dielectric substrate with relative permittivity and thickness. The patch can be, for instance, fed with a probe feed coming from the ground plane. One limitation of these antennas is that they are generally narrow band, and a good way of approximating the bandwidth is to determine Q factor, which is inversely proportional to fractional bandwidth. Therefore, the goal of this paper is to determine tight, lower Q factor bounds for microstrip patch antennas within a given design region, and we choose this design region to be a rectangular design region. And then using current optimization, we determine the lower Q factor bounds within this design region. And here are some classical patch geometries that can fit within this design region. So for this example, we consider this constraint on the patch design region with this dielectric thickness. And then we're going to represent the bounds with respect to the patch design region dimension normalized by the free space wavelength. So let's first take a look at the shoe limit, which considers a spherical design region. And what we see when we compare this to our bounds with having a relative permittivity of 1 for the substrate, there's orders of magnitude difference. And further, we can see that the half wavelength resonant patches for both polarizations are effectively on the bounds. And when we look then at some miniaturized patch geometries, we see that they are also effectively on top of the bounds. And now when we take a look at the bounds for relative permittivity of 2, we again see that these geometries are on top of the bounds. And here it should be noted that, of course, the resonances shift with respect to the wavelength inside the substrate. And when we take a look at the relative permittivity of 4 for the substrate, we again see the same. And here we should note again that for all of these cases, the bounds are orders of magnitude tighter than the shoe limit. So to summarize, we've been able to show new lower Q factor bounds based on current optimization. Classical patch geometries are shown to be on top of the bounds. The bounds are orders of magnitude tighter than the shoe limit. Further, if you look in the paper, you will find a simple method that we propose for approximating the bounds using commercial solvers, and we also add polarization constraints to the bounds. And with that, I thank you for listening, and I hope you find the time to read the paper.
It is known that co-polarized in-band full-duplex antennas are now receiving more attention because they can theoretically double the spectral efficiency over that of dual-polarized antennas. In our previous work, a two-port dielectric and resonator antenna was proposed. The decoupling effect was achieved without any additional structure. However, the decoupling bandwidth of the antenna was relatively narrow. To address this problem, a two-port stocky patch antenna is designed here. The perspective view of a conventional two-port patch antenna is shown here. Only two narrowband characteristic modes resonate at 3.3 GHz and 4.2 GHz, while only CN1 can be excited by pulse. Therefore, the same current magnitude at the receiving and transmitting ports results in a high coupling level, which is higher than -2.5 dB over the passband. Next, a patch antenna is suspended 12 mm above the ground. A new characteristic mode, CM2, is introduced due to the loading effect of the probe. When the left probe is excited, CM1 and CM2 are excited simultaneously, so that the current around the right probes will be cancelled out. The simulated S parameter supports our conclusion. However, the antenna in case 2 suffers from a narrow decoupling bandwidth. To address this issue, another rectangular patch is suspended above the antenna in case 2, which leads to the evolution into case 3. A new characteristic mode, CM4, corresponding to the TM01 mode of the stocky patch antenna, is introduced. A trip-mode operating scheme is proposed to demonstrate the broadband decoupling phenomenon in case 3. For each mode pair, if the two modes are excited simultaneously, then the coupling energies of the receiving ports with the same amplitude and opposite phase will cancel each other out. Therefore, two transmission zeros are generated separately in the center of the mode pairs. The final proposed antenna can operate from 3.3 GHz to 4.2 GHz and achieve a 20 dB pulse isolation level throughout passband. The fabricated antenna is depicted here. The measured results agree well with the simulated ones. In this communication, a trip mode operation decoupling scheme is first proposed to improve the bandwidth and isolation level of the two-port Stucky patch antenna. The proposed antenna achieves wide decoupling bandwidth while not needing to be reshaped or extended compared with the traditional single-port patch antenna.
Hello, everyone. It is my pleasure to introduce our research on a wideband dual circularly polarized series fed corner-truncated patch array using coplanar proximity coupling. The geometry of the proposed wideband proximity coupled series fed dual CP antenna is shown in this figure. It is composed of a cross-shaped arrangement of corner-truncated patch array serving as the radiator, a folded microstrip line, and two tapered microstrip lines acting as the feeding structure, and a soft surface structure for radiation pattern improvement. Compared with the existing works in series fed dual CP antenna designs, the contributions of this work are summarized as follows. First, the corner-truncated patch array is for the first time used in designing an proximity-coupled series-fed dual CP antenna. Besides, it effectively resolves the problem of narrow operating bandwidth for the previous single-layer series-fed dual CP antennas, while maintaining a high antenna efficiency simultaneously. Furthermore, the proposed antenna achieves stable boresight radiation across a wide operating bandwidth, effectively mitigating the common beam deflection issue in previous coplanar single-layer series-fed dual CP antennas. Compared with the existing series-fed dual CP designs, the proposed design achieves attractive features of simple structure, wide operating bandwidth, high antenna efficiency, and low cost. This page shows the design evolution and operating mechanism of the proposed antenna. At first, the proximity-coupled series-fed technique has been introduced for the boresight dual CP operation at a lower operating frequency, which is indicated as antenna 1. Then, we introduce the inner patch group and corner truncation, which are indicated as antenna 2 and antenna 3, respectively. By this way, the coupled power for the 4 outer patch group elements becomes more balanced, as shown in the figure of current density distribution. Thus, the operating bandwidth has been improved in antenna 2 and further in antenna 3. At last, in proposed antenna, a soft surface structure has been incorporated to improve radiation pattern at a higher operating frequency. When utilizing the soft surface structure, the surface electric field is predominantly confined within the structure itself and exhibits a relatively uniform distribution. The proposed wideband proximity-coupled series-fed antenna has been simulated, and a prototype has been fabricated and measured. Here are the simulated S parameter and axial ratio when port 1 is excited. Taking into account the 10 dB impedance bandwidth, 15 dB isolation bandwidth, and the 3 dB axial ratio bandwidth, the operating bandwidth of the proposed antenna is 18.5% in experimental measurement. The radiation performances of the antenna are shown in this page. It can be seen that the proposed antenna maintains stable boresight CP radiation characteristics at the 3 frequencies across the operating band. Across the operating band, the measured realized gains range from 6.82 to 8.48 dBIC. The measured total efficiencies range from 74% to 85.5%. More details can be found in the references. Thanks for your listening.